In the last video, part 1 of curve fitting using the least squares regression, I explained curve fitting for linear functions. In this video, part 2 of curve fitting using the least squares regression, I will explain how to linearize a nonlinear function and apply the least squares regression. The nonlinear functions to be explained are the exponential function and the Fourier series. The nonlinear functions, which can't be linearized, will be explained in the next video, curve fitting by least squares regression, part 3. Least squares regression by linearization will be explained for the exponential function and Fourier series. In the exponential function, I will explain linearization by logarithm and least squares regression and parameter calculation. In the Fourier series, I will explain how to analyze data distribution, how to select trigonometric function depending on data distribution, and finally least squares regression application. Here, I have a quiz for you. If you watch this video till the end, you will get the answer right away. What is the Fourier series that matches the waveform on the left? All coefficients included in the following equations are non-zero. Please choose one correct answer. Should I choose the sine function? Or should I choose the cosine function? The average value for numbers 1 to 4 is 0, and the average value for numbers 5 and 6 is 3. Understanding the shape of the waveform can help you find the right answer. Although the exponential function is not a linear function, linearizing it allows us to use the least squares regression for curve fitting. For example, the oscillation of an undamped 1 degree of freedom system can be expressed in equation 1. If equation 1 is represented on a graph, it becomes a sine waveform with a constant amplitude as shown in the figure to the right. When damping is added to a 1 degree vibration system, the damped vibration of a 1 degree of freedom system can be expressed in equation 2. This expression represents the magnitude of vibration that changes with time x for a system with 1 degree of freedom and damping. The magnitude of vibration can be displacement, velocity, or acceleration. This can be expressed as the product of an exponential function and a trigonometric function, and when expressed graphically, it appears as a blue curve in the lower right picture. If you connect the peaks that change with time as shown in the figure on the right, you get equation 3, which can be expressed as the green curve. The green curve in equation 3 is the product of the coefficient a and the exponent part of equation 2. If a is c1 and minus zeta omega n is c2, we can linearize the exponential function. The derivation process of this equation will be covered in the next vibration noise video, and in this video, we will focus on how to find C1 and C2. The way to linearize an exponential function is to use a logarithmic function to create the exponential part in the form of a coefficient. For example, let's linearize an exponential function like equation 4. If we take the natural logarithm of both sides of equation 4, we can get equation 5. By substituting natural log y in equation 5 with z, natural log c1 with c3, and minus c2 with c4, we can obtain equation 6. If natural logarithm y is expressed in a logarithmic scale on the vertical axis, equation 5 can be expressed as a linear straight line, as shown in the lower right figure. Since equation 6 is in linear form, the least squares method can be applied. Apply the least squares method to find z, c3, and c4, and then, from these values, we can calculate y, c1, and c2, as shown in equation 7, equation 8, and equation 9. Let's solve an example of an exponential function. The measurement data in the example are for sets as shown in the table below left. If this is expressed graphically, it looks like the graph on the left. The system function is expressed in equation 4 and is already known. In order to linearize the system function, equation 5 can be obtained by taking the natural logarithm of both sides. If natural log y is z, natural log c1 is c3, and minus c2 is c4, equation 5 can be expressed as equation 6. Since equation 6 is in linear form, the least squares regress explained previously can be used. Since the natural log is taken on both sides, the dependent variable z in equation 6 is the natural log y and can be calculated as shown in the table on the right. First, as explained earlier, the data is transformed to fit a linear system function. The z value of equation 6, which is the natural logarithm of data y, can be obtained as shown in the table on the left. The residual expression for the system function equation 6 can be expressed as equation 10. Therefore, the square function of the residual can be expressed as equation 11. If you perform a partial differentiation of equation 11 with respect to the unknown coefficient C4, you can obtain equation 12, and if you perform a partial differentiation with respect to C3, you can obtain equation 13. By rearranging equation 12, we can get equation 14, and by rearranging equation 13, we can get equation 15. By solving these two equations 14 and 15, we can obtain the two coefficients C3 and C4. Equations 14 and 15 represent normal equations. If you calculate the sigma function in equation 14 and equation 15 using the values in the table shown on the upper left, you can obtain the result in equation 16. By substituting the result of equation 16 into equation 14 and equation 15 and organizing, we can obtain normal equations equation 17 and equation 18. From these two normal equations, the coefficients C3 and C4 can be calculated as equation 19. Continuing, by substituting C3 and C4 of equation 19 into equation 6 and rearranging, we can obtain the result of equation 20. Since the system function equation 20 is the result of taking the natural logarithm of the original system function, the coefficients C3 and C4 shown in equation 19 must be converted to the original coefficients C1 and C2 through a mathematical calculation process. C3 and C4 were obtained as in equation 19, and from this, the linear system function was obtained as in equation 20. From C3 and C4 in equation 19, C1 and C2 in equation 4 can be obtained. By substituting C3 into equation 8, C1 can be calculated as equation 21. Next, by substituting C4 into equation 9, C2 can be calculated as in equation 22. Therefore, the final result system function of curve fitting using the least squares method can be expressed as equation 23 by substituting C1 in equation 21 and C2 in equation 22 into equation 4. Equation 23 is the system function that is the final result we want to find. Although the system function is nonlinear, we were able to use the least squares method by taking the natural logarithm of both sides and obtain the system function for the nonlinear function. For the previous example, you can get the same result by using the matrix equation. The process of taking natural logarithms and converting them to linear form is the same. Next, if we change the previous equation to the form of the fx function, we get equation 24. Therefore, the fx function can be obtained as equation 25. The C matrix of normal equation 26 obtained in the previous video E0066 can be expressed by equation 27. The Z matrix can be calculated by equation 28. The F matrix can be calculated by equation 29. And the FT matrix can be calculated by equation 30. By substituting all four equations from equations 27 to 30 into equation 26 and finding the unknown coefficients C3 and C4, the linear system function equation 20 can be obtained, which can be seen to be the same as the result obtained without using the matrix previously. Next, we will learn how to apply the least squares method when the system function is a periodic function. A periodic function is a function that repeats the same shape periodically. For example, the top picture shows the periodic function of a square wave, and the bottom picture shows the periodic function of a sawtooth wave. For both functions, the basic waveform of one cycle can be expressed as 0 to p, or p to 2p, or 2p to 3p, and they all have the same shape. Representative periodic functions are trigonometric functions. The basic period of the sine and cosine functions is 2 pi. The graph of sine 2x, shown in orange, has a period of pi, and the graph of sine for x, shown in grey, has a period of pi divided by 2. Likewise, the graph of cosine x, shown in blue, has a period of 2 pi. The graph of cosine 2x, shown in orange, has a period of pi, and cosine for x, shown in grey, has a period of pi divided by 2. As the constant value of variable x increases, the period decreases. Even if it is not the square wave or sawtooth waveform we looked at earlier, if it repeats periodically, it is a periodic function. The top figure represents a periodic function with period of p. The function that repeats the arbitrary shape shown at the top is also a periodic function, and the sine function in the middle picture and the cosine function in the bottom picture are also periodic functions with a period of 2 pi. All periodic functions can be expressed as the sum of a sine function and a cosine function, which is called a Fourier series. As explained earlier, all periodic functions can be expressed as the sum of a sine function and a cosine function. This can be expressed as equation 32. Equation 32 is called Fourier series. The constants of 0, an, and bn in equation 32 are called Fourier constants. The constant of 0 can be obtained from equation 33, and the constant value an of the cosine function can be obtained from equation 34. Additionally, the constant value bn of the sine function can be obtained from equation 35. Equation 33, equation 34, and equation 35, which calculate the Fourier constant value, are called Euler formulas. The Euler formulas explained earlier can be derived using the orthogonality property of trigonometric functions. The trigonometric function system consists of each sine and cosine element expressed in equation 36. First, we randomly select any two elements shown in equation 36. This also includes selecting the same element twice. When the result of multiplying the two selected functions is integrated over one arbitrary cycle, all elements become 0 except in the case where the two elements are the same function and m and n are the same integer. The cases where these integrals become 0 can be expressed in three ways: equation 37, equation 38, and equation 39. The integration period can be arbitrarily set to 1 period. As shown here, you can set it from minus pi to plus pi, or you can set it from 3 pi to 5 pi. The orthogonality of trigonometric functions, as shown in equation 37, equation 38, and equation 39, means that if the result of multiplying any two elements in equation 36 is integrated over one period, all of them are 0. This can be easily proven using the formula for converting the products of trigonometric functions into sums. Additionally, it can be easily understood by drawing a graph of the function in the integration section. Since the method of proving it mathematically is found in many textbooks, here we will first explain how to understand it visually through a graph of the integration interval. For example, we chose two cosine functions arbitrarily in the trigonometric system shown in equation 36. These are cosine x on the top left and cosine 2x on the bottom left, respectively. Let's multiply these two functions y1 and y2 and call the resulting function fx. If fx is graphed, it will look like the figure on the right. This graph is symmetrical about line x equals pi, and as can be intuitively seen, the result of the integration is 0. In the figure, areas with the same color are equal and have opposite signs, so the integration result is 0. That is, plus red area equals minus red 1, plus green area equals minus green 1, plus black area equals minus black 1, and plus yellow area equals minus yellow 1. In other words, the areas are the same and the signs are opposite, so the integration result has a 0 value. In a trigonometric system, no matter which cosine function you choose, if the constants in front of the x are different, the integral result will be 0. Next, let us choose two arbitrary sine functions from the trigonometric system represented by equation 36. Each of these is the upper left figure, sine x, and the lower left figure, sine 2x. After multiplying these two functions y1 and y2, let's call the resulting function fx. If fx is graphed, it will look like the figure on the right. This graph is symmetrical about the line x equals pi, and as can be intuitively seen, the result of the integration is 0. In the figure, areas with the same color are equal and have opposite signs, so the result of the integration is 0. In other words, plus red area equals minus red 1 and plus green area equals minus green 1, so the areas are the same and the signs are opposite, so the integration result has a 0 value. In a trigonometric system, no matter which sine function you choose, if the constants in front of the x are different, the integration result will be 0. This time, we will choose one arbitrary cosine function and one arbitrary sine function from the trigonometric system shown in equation 36. Each of these is cosine x on the top left and sine x on the bottom left. After multiplying these two functions y1 and y2, we will call the resulting function fx. If you graph fx, it will look like the figure on the right. This graph is asymmetric about the line x equal pi, and as can be intuitively seen, the result of the integration is 0. In the figure, areas with the same color are equal and have opposite signs, so the result of the integration is 0. In other words, plus red area equals minus red 1 and plus green area is minus green 1, so the areas are the same and the signs are opposite, so the integration result has a 0 value. No matter which functions you choose in a trigonometric system, if one is a cosine function and the other is a sine function, the result of the integration is 0. This time, let's assume that we choose two identical cosine functions from the trigonometric system shown in equation 36. These are cosine x in the top left figure and cosine x in the bottom left figure, respectively. After multiplying these two functions y1 and y2, we will call the resulting function fx. If you graph fx, it will look like the figure on the right. This graph is symmetric about the line x equal pi, and as can be intuitively seen, the integration result is not 0. As shown in the figure, all graph lines lie above the x-axis, so the integration result is not 0. No matter which function you choose in a trigonometric system, if the two functions are exactly the same, the integration result will not be 0. This time, let's assume that we choose two identical sine functions from the trigonometric system shown in equation 36. Let's call them sine x in the upper left figure and sine x in the lower left figure, respectively. After multiplying these two functions y1 and y2, we will call the resulting function fx. If you graph fx, it will look like the figure on the right. This graph is symmetric about the line x equals pi, and as can be intuitively seen, the integration result is not 0. As shown in the figure, all graph lines exist above the x-axis, so the integration result is not 0. No matter which function you choose in a trigonometric system, if the two functions are exactly the same, the integration result will not be 0. This time, we will prove Euler's formula using mathematical equations. First, let us derive the expression for the constant A0 of Euler's formula, expressed in equation 33. By integrating both sides of equation 32 from minus pi to plus pi, it can be expressed as equation 40. By rearranging the sigma function and integral function, we can obtain equation 41. When cosine nx is integrated in equation 41, as shown in the figure on the right, the integrated value of up to 2 pi over n of one cycle section is 0, so the integrated value from minus pi to plus pi is also 0. Also, when integrating sine x, as shown in the figure below right, the integrated value of 2 pi over n of one cycle is 0, so the integrated value from minus pi to plus pi is also 0. Therefore, all sigma function terms are eliminated, and the integral on the right side of equation 40 becomes 2 pi a0. By rearranging equation 42, a0 can be expressed as equation 33. In Fourier series, a 0 represents the average value. As shown in the figure, when the average value as 0 is 0, function y1 can be represented by the blue graph sine nx. When the average value as 0 is 3 instead of 0, it becomes a red graph, 3 plus sine nx, and when the average value as 0 is minus 3, it becomes a green graph, minus 3 plus sine nx. Therefore, in this example, a 0 means shift distance of sin nx along the vertical direction. Next, let us prove Euler's formula for an, which is the coefficient of the cosine function. Equation 43 can be obtained by multiplying both sides of equation 32 obtained previously by cosine mx and integrating both sides from minus pi to plus pi respectively. By rearranging the integral function and sigma function in equation 43, it can be expressed as equation 44. In equation 44, the integral term of cosine, the first term on the right-hand side, is 0 because m is a positive integer. If n and m do not have the same value, the integral value of the product of the cosine functions, which is the first integral term of the sigma function, is 0 as shown in the upper right figure, and if they have the same value, it is not 0 as shown in the lower right figure. Therefore, everything disappears except when n and m are the same. The product of sine and cosine, which is the second integral term of the sigma function, disappears because the integral value of the product of sine n and cosine m are 0 regardless of whether n and m are the same or different. Therefore, in the first term of the sigma function, all but the case where m and n are equal disappear. If you integrate this and organize it, it can be expressed as equation 45, and if you organize it for an, you can get the Euler formula for an as shown in equation 34. Next, let us prove Euler's formula for the coefficients of the sine function. Equation 46 can be obtained by multiplying both sides of equation 32 obtained previously by sine mx and integrating both sides from minus pi to plus pi respectively. By rearranging the integral function and sigma function in equation 46, it can be expressed as equation 47. In equation 47, the integral term of the sine, which is the first term on the right side, is 0 because m is a positive integer. The first integral term of the sigma function, the product of sine and cosine, disappears because the integral value of the product of sine n and cosine m are 0, regardless of whether n and m are the same or different. If n and m do not have the same value, the integral value of the product of the sine function, which is the second integral term of the sigma function, is 0 as shown in the upper right figure, and if they have the same value, it is not 0 as shown in the lower right figure. Therefore, everything disappears except when n and m are the same. Therefore, in the second term of the sigma function, all but the case where m and n are equal disappear. If you integrate this and organize it, it can be expressed as equation 48, and if you organize it for Bn, you can get the Euler formula for Bn as shown in equation 35. The Fourier series so far has looked at the case where the fundamental period is 2 pi. However, In reality, the fundamental period we encounter in life is not 2 pi but has an arbitrary value. The strings of a stringed instrument, or the surfaces of a percussion instrument, have a given length value, not 2 pi. Therefore, in order to model these mathematically, it is necessary to express a function with an arbitrary period other than 2 pi in the form of a trigonometric function. The Fourier series with fundamental period 2 pi can be expressed as equation 32, as seen previously, and the Euler formula of the coefficients in equation 32 can be expressed as equations 33, 34, and 35. On the other hand, a periodic function with an arbitrary period of 2L instead of a period of 2 pi can be expressed as a Fourier series as shown in equation 49. The Euler formulas for Fourier coefficient are 0, an, and bn can be expressed as equations 50, 51, and 52. For example, consider modeling the length of an instrument as a trigonometric function. In the case of a violin, the length of the violin strings is Lv and the fundamental period is 2Lv. In the case of the tambourine, the diameter of the expression is Lt and the fundamental period is 2Lt. In the case of these instruments, the movement of the string or surface, i.e. vibration, can be expressed as a trigonometric function using Lv and Lt, which are half of the fundamental period. The smaller the length or area of the string or surface and the greater the tension of the string and surface, the greater the number of vibrations per second and the higher the pitch of the sound. Let us learn how to represent periodic functions with arbitrary period 2L as trigonometric functions. If an arbitrary period is 2L, the period of the trigonometric function is 2 pi, so the value corresponding to pi is L, which is half the period. Therefore, a periodic function with an arbitrary period of 2 can be expressed as equation 53. In equation 53, if x is L, the function value is sine pi, and if x is 2L, then sine 2 pi, if x is 3L, then sine 3 pi, and if x is 4L, then sine 4 pi, and so on. To understand the Fourier series, let's represent the square waveform as shown in the figure on the right as a Fourier series. The square waveform in the figure can be expressed as equation 54. From the picture, we can see that the period of the square waveform is 4, and intuitively the average value is 1. In Fourier series, A0 represents the average value, so the value of A0 is 1. Additionally, the square waveform in the picture is symmetrical about the fx axis, which is the line x equals 0. In trigonometric functions, the function that is symmetric about the fx axis is the cosine function, so we can see that the Fourier series can be expressed as a cosine series without a sine series. By substituting equation 54 of the square wave into equations 50, 51, and 52 of the Euler formula to obtain A0, An, and Bn, we can obtain the result of equation 55. Let's look at their calculation process in detail. First, let's find A0 using Euler's formula 50. The period of the square waveform is 4 and L is half the period, so the value of L is 2. By substituting the value of the fx function in equation 54 into equation 50 and calculating the integral equation for each section, equation 56 can be obtained. The values of the first and third terms of equation 56 are 0, and by integrating the second term, the integration result of equation 57 can be obtained. Therefore, we can see that the value of A0 is the integral value, 1, as shown in equation 58. Next, let's find An using Euler's formula 51. As before, the period of the square wave is 4 and L is half the period, so it is 2. By substituting the value of the fx function in equation 54 into equation 51 and calculating the integral equation for each section, equation 59 can be obtained. The values of the first and third terms of equation 59 are 0, and if you integrate the second term, you can obtain the integral values for an, as shown in equation 60, and these values are the coefficients of the cosine series. By sequentially substituting values such as 1, 2, 3, 4, and 5 for n in equation 60, the an values can be obtained, respectively, as shown in equation 61. Here, we can see that when n is an even number, the coefficient an values are all 0. This time, let's find Bn using Euler's formula 52. As before, the period of the square wave is 4 and L is half the period, so it is 2. By substituting the value of the fx function in equation 54 into equation 52 and expressing the integral equation for each section, equation 62 can be obtained. The first and third terms of equation 62 are 0, and integrating the second term gives the integral value of 0, as shown in equation 63. Therefore, as shown in equation 64, for all positive integer values of n, Bn is 0, resulting in all sine series disappearing. By substituting the a0 of equation 58, an of equation 61, and Bn of equation 64 obtained so far into equation 49, we can obtain the Fourier series f of equation 55 for the square waveform. As predicted earlier, since the average value is 1, the value of a0 is 1, and since it is symmetrical about the fx axis, we can see that all sine functions have disappeared. Let's continue to find out what equation 55 means. If you add the first term, equation 65, and the second term, equation 66, shown in yellow in equation 55, you get equation 67. If you represent it graphically, you can get the result shown in the blue graph on the right. Here, the red graph represents the square waveform we want to display. The blue graph representing fp2 in equation 67 is the result of adding 1 to the cosine function f2x in equation 66, so it is the same as the result of the cosine function in equation 66 being vertically shifted by 1 in the positive direction of the vertical axis. Although it is different from the square wave graph, you can see that it has a roughly approximate shape. The third term of the Fourier series can be expressed as f3x as shown in equation 68. By adding equation 68 to equation 67 obtained previously, the sum fp3 of the third term of Fourier series equation 55 can be obtained as equation 69. If equation 69 is graphed, it becomes the blue line in the picture on the right. As shown in the figure, compared to the sum fpe of the second term of the Fourier series, the result is much closer to a square wave. This means that the overall error value of the Fourier series is decreasing. Continuing, the fourth term of the Fourier series can be expressed as f for x as equation 70. By adding equation 70 to equation 69 obtained previously, the sum of fp for up to the fourth term of Fourier series equation 55 can be obtained as equation 71. If equation 71 is graphed, it becomes the blue line in the picture on the right. As shown in the figure, compared to the sum fp3 of the previous Fourier series third term, it can be seen that the result is much closer to a square waveform. This means that the overall error value of the Fourier series continues to decrease as the terms of the Fourier series increase. Continuing, the fifth term of the Fourier series can be expressed as f5x as shown in equation 72. By adding equation 72 to equation 71 obtained previously, the sum fp5 of up to the fifth term of Fourier series equation 55 can be obtained as equation 73. If equation 73 is graphed, it becomes the blue line in the picture on the right. As shown in the figure, compared to the sum fp4 of the fourth term of the Fourier series, the result is much closer to a square wave. This means that the overall error value of the Fourier series continues to decrease as the terms of the Fourier series increase. Continuing, The sixth term of the Fourier series can be expressed as f6x as shown in equation 74. By adding equation 74 to equation 73 obtained previously, the sum fp6 of up to the sixth term of Fourier series equation 55 can be obtained as equation 75. If equation 75 is graphed, it becomes the blue line in the picture on the right. As shown in the figure, compared to the sum of fp5 up to the fifth term of the Fourier series, the result is much closer to a square wave. This means that the overall error value of the Fourier series continues to decrease as the terms of the Fourier series increase. Let's learn about the fundamental period and fundamental frequency. The fundamental period is the period of the trigonometric function with the largest period among the trigonometric functions of the Fourier series, and the fundamental frequency is the frequency of the trigonometric function with the smallest frequency among the trigonometric functions of the Fourier series. The trigonometric function with the largest period and the trigonometric function with the smallest frequency are the same trigonometric function. Since the fundamental period of a trigonometric function is 2 pi, the fundamental period of the Fourier series can be obtained from the largest periodic function in equation 55 using equation 55a. In the case of the picture, the fundamental period is 4. The fundamental frequency is the reciprocal of the fundamental period, so it is 0.25. As shown on the right, the fundamental period and frequency are called by various names such as fundamental, primitive, basic, and prime. This time, we will look at unsymmetric square waveforms. Unlike a square waveform that is symmetrical about the fx axis, the square waveform shown on the right is not symmetrical about the fx axis. The black square waveform in the figure on the right can be seen as having shifted the square waveform shown in red in the positive direction by 1 along the vertical axis. Also, from the figure, we can see that the period of the square wave is 4, and intuitively the average value is 1. The red square waveform is an odd function, and when it is expressed as a Fourier series, all cosine series, which are even functions, disappear, and only the sine series, which is an odd function, remains. Since the black graph is the red graph plus 1, the Fourier series for the black square waveform can be expressed as a series sine with the average value 1, as shown in equation 77. The process of calculating A0, AN, and Bn in equation 77 can be obtained using the same process as for the symmetrical square waveform seen earlier. Let's take a closer look at their calculation process. First, let's find A0 using Euler's formula, 50. The period of a square wave is 4, and L is half the period, so it is 2. By substituting the value of the fx function in equation 76 into equation 50 and calculating the integral equation for each section, equation 78 can be obtained. The value of the first term in equation 78 is 0, and if you integrate the second term, you can get the integration result in equation 79. Therefore, as shown in equation 80, the value of A0 is 1. Next, let's find AN using Euler's formula 51. As before, the period of the square wave is 4 and L is half the period, so it is 2. By substituting the value of the fx function in equation 76 into equation 51 and calculating the integral equation for each section, equation 81 can be obtained. The value of the first term in equation 81 is 0, and integrating the second term gives the integral value of 0, as shown in equation 82. Therefore, as shown in equation 83, for all positive integer values of n, an is 0, and consequently all cosine series disappear. This time, let's find Bn using Euler's formula, 52. As before, the period of the square wave is 4 and L is half the period, so it is 2. By substituting the value of the fx function in equation 76 into equation 52 and expressing the integral equation for each section, equation 84 can be obtained. If the value of the first term in equation 84 is 0 and the second term is integrated, the integration result can be obtained as shown in equation 85. By sequentially substituting values such as 1, 2, 3, 4, and 5 for n in equation 85, you can obtain all Bn values of each term of the Fourier series, as shown in equation 86. Here, we can see that when n is an even number, the coefficient Bn values are all 0. By substituting the A0 of equation 80, An of equation 83, and Bn of equation 86 obtained so far into equation 49, we can obtain the Fourier series f of equation 77 for the square waveform. As predicted earlier, since the average value is 1, the value of A0 is 1, and the square waveform minus the average value 1, which is red square wave, is point symmetrical with respect to the origin, so we can see that all cosine functions have disappeared. Let's continue to find out what equation 77 means. If you add the first term, equation 87, and the second term, equation 88, shown in yellow in equation 77, you get equation 89. If you represent it graphically, you can get the result shown in the blue graph on the right. Here, the red graph represents the square waveform we want to display. The blue graph representing fp2 in equation 89 is the result of adding 1 to the cosine function in equation 88, so it is the same as the result of the cosine function in equation 88 being vertically shifted by 1 in the positive direction of the vertical axis. Although it is different from the square wave graph, you can see that it has a roughly approximate shape. The third term of the Fourier series is f3x and can be expressed as equation 90. By adding equation 90 to equation 89 obtained previously, the sum fp3 up to the third term of Fourier series equation 77 can be obtained as equation 91. If equation 91 is graphed, it becomes the blue line in the figure on the right. As shown in the figure, compared to the sum fp2 of the previous Fourier series second term, it can be seen that the result is much closer to a square waveform. This means that the overall error value of the Fourier series is decreasing. Continuing, the fourth term of the Fourier series can be expressed as f for x as in equation 92. By adding equation 92 to equation 91 obtained previously, the sum fp4 of up to the fourth term of Fourier series equation 77 can be obtained as equation 93. If equation 93 is graphed, it becomes the blue line in the figure on the right. As shown in the figure, compared to the sum fp3 of the previous Fourier series third term, it can be seen that the result is much closer to a square waveform. This means that the overall error value of the Fourier series continues to decrease as the terms of the Fourier series increase. Continuing, the fifth term of the Fourier series can be expressed as f5x as shown in equation 94. By adding equation 94 to equation 93 obtained previously, the sum fp5 of up to the fifth term of Fourier series equation 77 can be obtained as equation 95. If equation 95 is graphed, it becomes the blue line in the figure on the right. As shown in the figure, compared to the sum fp4 of the fourth term of the Fourier series, the result is much closer to a square wave. This means that the overall error value of the Fourier series continues to decrease as the terms of the Fourier series increase. Continuing, the sixth term of the Fourier series can be expressed as f6x as shown in equation 96. By adding equation 96 to equation 95 obtained previously, the sum fp6 of up to the sixth term of Fourier series equation 77 can be obtained as equation 97. If equation 97 is graphed, it becomes the blue line in the figure on the right. As shown in the figure, compared to the sum of fp5 up to the fifth term of the Fourier series, the result is much closer to a square wave. This means that the overall error value of the Fourier series continues to decrease as the terms of the Fourier series increase. Let's find out what even functions and odd functions are. what their characteristics are, and how to use them. First, let's learn about even functions. If the average value of the previously discussed function is 0 and is symmetrical about the fx axis, the square waveform can be expressed as equation 99 using the remaining terms except for average terms plus 1 in equations 55a and minus 1 in equation 55b. If this is graphed, it becomes the black waveform in the figure. As shown in the figure, a function that is symmetrical about the fx axis is called an even function. When you find the Fourier series for an even function, all sine series become 0, and only the cosine series remains. Even in all cases where the even function moves vertically, if the Fourier series is obtained, only the cosine series and constant value that represent the average value for the vertical movement remain, as shown in equation 55a and 55b. From what we have seen above, you can decide which Fourier series to select based on the distribution shape of the data. The black dots in the figure represent the coordinates of the data. If the data distribution in the figure here is continuously repeated, the period is 4, the average value is approximately 0, and you can see that it is an even function with a symmetrical distribution about the fx axis. When you find the Fourier series for the even function, as shown in equation 99, all sine series are 0 and only the cosine series remains. At this time, the first term of the Fourier series can be expressed as equation 100, and when represented graphically, it is a cosine function that has the shape of a green graph. However, there is a question here. Why are there only odd terms, such as pi, 3 pi, 5 pi, etc., and why are the even terms, such as 2 pi, 4 pi, etc., missing? Let's understand this by enlarging the yellow shaded part in the figure. The yellow and light green shaded areas in the figure respectively represent the regions of the half cycle. The black dots in the figure represent the coordinates of the data. Equation 100 is the first term of the Fourier series. Equation 101 is the missing even term in the Fourier series equation 99. And equation 102 is the second odd term of the Fourier series. What you need to know here is that the first cosine function shown in green is an even function, but when viewed from the domain of the half cycle L, it is point symmetrical with respect to point 10, so it is the shape of an odd function in half a cycle L. Since the data distribution is approximately point symmetrical with respect to point 10, it can be seen that a function in the shape of an odd function must be used in the half cycle. As shown in the figure, looking at the half cycle area, it can be seen that y1 and y3 are odd function shapes that are point symmetrical about point 10, and y2 has the shape of an even function that is symmetrical about the line x equals 1. Therefore, y2, which has the shape of an even function in half the cycle, has 0 contribution to the data that has the shape of an odd function, so it is omitted from equation 99. This time, we will learn about odd functions. A square waveform with the conditions in equation 103 can be represented by the black graph in the upper right figure. This square waveform has 0 mean value, is point symmetric about the origin, and can be written as a Fourier series in equation 104. As shown in the figure, a function that is point symmetrical about the origin is called an odd function. When we find the Fourier series for the odd function, all cosine series become 0, leaving only the sine series. Even in all cases where the odd function moves vertically, if you find the Fourier series, only the constant value and sine series for the vertical movement remain, such as equation 77a or 77b. The red graph in the figure represents equation 77a, which is the result of the square waveform in equation 104 being shifted by 1 in the positive direction. This is the same as equation 104 with the average value, 1, added. Additionally, the blue graph in the figure represents equation 77b, which represents the result of the square waveform in equation 104 being shifted by 1 in the minus direction. In this case, it is equivalent to subtracting the average value of 1 from equation 104. Next, let's look at the process of deciding which Fourier series to select based on the distribution shape of the data. The black dots in the figure represent the coordinates of the data. If the data distribution in the figure here is continuously repeated, the period is 4, the average value is approximately 0, and you can see that it is an odd function with a point-symmetric distribution about the origin. When the Fourier series is obtained for the odd function, as shown in equation 104, all cosine series are 0 and only the sine series remains. At this time, the first term of the Fourier series can be expressed as equation 105, and when represented graphically, it is a sine function that has the shape of a green graph. However, there is a question here. Why are there only odd terms such as pi, 3 pi, 5 pi, etc., but are the even terms such as 2 pi, 4 pi, etc. missing? Let's understand this by enlarging the yellow shaded part in the figure. The yellow and light green shaded areas in the figure respectively represent the regions of the half cycle. The black dots in the figure represent the coordinates of the data. Equation 105 is the first term of the Fourier series. Equation 106 is the even term missing from the Fourier series equation 104. And equation 107 is the second odd term of the Fourier series. What you need to know here is that the sine function is an odd function, but when viewed from the area of the half cycle L, it is symmetrical with respect to the straight line of x equal 1, so it is the shape of the even function in half a cycle L. Since the data distribution is approximately symmetrical with respect to the straight line as shown in the figure, when viewed in the half-cycle area, y1 and y3 are even function shapes that are symmetrical with respect to the straight line you can see. Therefore, y2, which has the shape of an odd function in the half-cycle, is omitted from equation 104 because its contribution to the data that has the shape of an even function is 0. Now that you understand the Fourier series, it's time to solve an example for least square regression. There is measurement data as shown in the table. The goal is to find a function that passes these data most closely. First, let's display the data in a rectangular coordinate system as shown in the figure on the right. From the shape of the data, intuitively, the average of all data is 0. It is point symmetrical about the origin, and repeats with a period of 4, so a Fourier sine series with a period of 4 is appropriate. As explained earlier, even sine functions such as b2, b4, etc. have no contribution and are therefore subtracted. Consequently, using the three-term sine function as shown in equation 108, the Fourier sine series b1, b3, and b5 that most closely pass through the given measurement data can be obtained. For convenience of explanation, we will calculate the coefficients of the Fourier series using only the yellow shaded portion of the measurement data. In the Fourier series example here, the three unknowns we need to find are b1, b3, and b5 in equation 108. Equation 109 will be a reference to find the functions of f1, f2, and f3. The three equations shown in equation 110 are element functions that make up the Fourier series to create the F matrix. You can create an F matrix by substituting the x values shown in the measurement data table into each of these three equations and organizing them. The remaining process is the same as for the linear functions, polynomial functions, and exponential functions we have already looked at. The coefficients b1, b3 and b5 of the Fourier series as a matrix equation. To create the normal equation 111 derived earlier, the elements of each matrix are first calculated. By substituting the x value from the measurement data in the table into equation 110, the F matrix can be obtained as equation 114. By transposing the F matrix, the F transpose matrix can be obtained as equation 115. The B matrix is the coefficients b1, B3 and B5 of the Fourier series that we need to find, and can be expressed as equation 112. Lastly, the Y matrix can be expressed as equation 113 using the fx value of the measurement data. By substituting equation 112 to 115 into the normal equation 111 and solving the equation using Gaussian-Jordan elimination, the coefficients B1, B3 and B5 of the Fourier series can be obtained as in equation 116. By substituting these coefficients into equation 108 above, we can obtain Fourier series equation 117 and our final goal is achieved. Now that we have obtained the Fourier series equation 117, let us simply graphically verify that the calculation has been performed correctly. First, the measurement data was displayed in a Cartesian coordinate system as a yellow dot. Next, the plot of fx obtained from equation 117 is shown. As shown in the figure, you can see that a square waveform with a period of 4 and an amplitude of 1 is well approximated by the Fourier function. The waveform of equation 117 changes significantly at the level of 1 and minus 1, but the amount of change can be reduced by increasing the Fourier series terms by adding 7 pi terms, 9 pi terms, and so on to equation 117. Let's find out the answers to the quiz. What Fourier series fits the waveform on the left? The correct answer is number 5. From the figure, you can see that the average value is 3, so answers 1 to 4 are not correct. Next, you can see that the square waveform in the figure is the result of a square waveform that is point symmetrical about the origin and shifted in the positive direction by 3 along the y-axis. Therefore, we need to use the sine function. From the above analysis, the answer is number 5. Let's summarize the contents. To obtain the coefficients of an exponential function using curve fitting by the least squares method, first linearize the coefficients using a logarithmic function. Next, calculate the linearized coefficient using the least square method in the same way as the linear function. Obtain the original coefficients from the calculated linearization coefficients. Next, to find the coefficient of the Fourier series, first determine whether the average of the data distribution is 0 or not, and also determine whether the data distribution is an even function or an odd function. If it is an even function, a cosine series is used, and if it is an odd function, a sine series is used to establish the Fourier series equation. If it is neither an even function nor an odd function, use both sine and cosine function, or alternatively move the origin along the x-axis to make it even or odd function, then apply least squares regression, and then move back the origin. Finally, the linearized coefficients are calculated and verified using the least square method. If you watch the previous videos, you can easily understand upcoming videos. In video number E0066 for of High Performance Driving Volume 5, which is Principle and Theory Part 5, I explained the importance of vehicle balance, understanding the mechanism of the vehicle, how to feel the vehicle, and the elements of high performance driving. Recently, in video number E0065 of Curve Fitting by Least Squares Regression Part 1, I explained the introduction and formulation of least squares regression for linear system. The next video is the third video of curve fitting using the least squares regression and will explain the curve fitting of the nonlinear system when its linearization is impossible. Please hit the thumbs up and catch the brand new videos by free subscription. So what are you waiting for? See you at next videos. Goodbye, guys.